It always helps. Repetition is the essence of learning, so let me practice that by giving a very brief summary. In the summary, will first be this difficult stuff that we did in the first hour last week, this renormalization group. I will not go through all of that again. Maybe I'll just give you one little thing on this other equation, the homogeneity equation, the nicest way perhaps to derive that, because some of you have been struggling with that. And then the infrared stuff. So we had seen the renormalization group equation, which has this nice form that the partial derivative with respect to explicit mu dependence is given by this derivative, and this is when you vary the implicit mu dependence sitting inside G. And then there is an overall factor called the anomalous dimension, that is the multiplicative factor, which depends on G. All of that acting on the endpoint renormalized Green's function, which depends on some in and outgoing momenta, the coupling, and possibly the scale mu explicitly, and that is 0. So in a sense, this is the way you can think about it. We have this Green's function gamma, and you can vary the arguments through varying mu, and you would like the variations to be 0, so you're looking for constant solutions of constant mu, and this equation tells you how you can trade off G variations against mu variations, such that the sum is still constant. That's sort of the content. Plus, we also have the homogeneity equation, homogeneity equation, which said that, which is a much more trivial equation in a sense. It says that this Green's function has a certain dimension that follows from having the dimensional parameters p and mu. And sorry, this is e to the t. Let me just make this nice. E to the t pi g and mu is 0. So this, sorry, not 0, is the canonical dimension of the Green's function. So this is actually, let me give you another brief of why this is and why you have this e to the t dimension. Now, what this says is that this has a certain dimension where momenta dimension 1, mu has dimension 1. Now, how can you get a certain dimension? Well, either through powers of mu or powers of p. But if it's a scalar, it's dot products of p. So you could have, for example, let's say mu to the power s. Let's focus on the mu combination first. Typically, there will be a term pi dot pj to the power r, such that the combination r plus s is exactly this gamma. That's the only way you can do it. There are no logarithms, it's only powers in dimensional regularization. So what I'll show you is that in this way you pick up precisely the r and the s dependence. So it's actually quite trivial. If you act with mu to the mu, if suppose this is one of the terms in gamma, in this gamma, act with mu to the mu on this expression, what do you get? S times that, right? S times that. Now, we rescale the t's, the pi's with this t, so you get really here e to the 2t. Right, now act with ddt. What do you get? Right. You get, what do you get? You get 2r. Huh? 2r times this, which is exactly the dimension of that term. Right, so you see that by acting with this derivative and that derivative, you exactly measure the canonical dimension of such terms, which is d gamma. So this is much simpler perhaps than you think. You can derive it infinitesimally as well, but perhaps this is the simplest way.
But scalings, one with lambda and one with t, because
no, all I want is well, all this equation says is how can I get this canonical dimension? And by splitting the variables, I can measure both the mu and the p dimensionality separately. And the sum must be equal to d gamma. And we had seen the solution. I'll repeat it so that the Green's function at we scaled momenta. If you want to know what the Green's function associated with your process is at high momenta, all you need to do is take your Green's function that you knew already at low momenta, but change the coupling now to the coupling not at the low scale but at the high scale. And mu, and multiply by this factor from 0 to t dt prime gamma tilde, which depends on this running coupling. And I had already indicated, and some of you asked, that this is a kind of resummation, in the sense that I could work this out if I can write this exponent to also in this form, so mu 0 to mu d mu prime over mu prime, because t goes like mu, like a log mu, up to a normalization constant. And then, for example, in the very lowest approximation, you keep only the lowest power of the anomalous dimension gamma 0, and you even fix the coupling at the lowest scale. So this only to show that if you then integrate, that gives you only a logarithm. You have a coupling times a logarithm sitting in the exponent. And if you then expand the exponent, you have an all-order series, meaning you have a resummation. So you have only done a few one-loop calculations to get all-order information. That's sort of the key thing to take along. All right, that was a bit about the renormalization group and what it can do for you. It's a powerful tool, and it's not an easy tool. I encourage you, though, to think about it, work with it, look at problems in field theory books, and it comes in many fields of theoretical physics, and it's an important step. We will be using it a little bit now then, but this is not the cornerstone on which the rest of the lectures is built. So if it's still hard to feel, I give up. The use is in understanding this bit of fundamental aspects of field theory, but we'll go back now to much more diagrammatic aspects. So we'd also look at ultraviolet power counting, now back to diagrams, where we had derived this very nice equation that if you have some very complicated loop integral, etc., that's the degree of divergence. Omega is simply 4 minus the number of external boson lines minus 3/2 the number of external fermion lines, no matter what happens inside. This really was a beautiful formula. And we'll use that a little bit later as well, but this is just to get you a bit thinking about how you can estimate superficially the degree of divergence. We had then left the field of ultraviolet divergences and really went to what makes QCD both very challenging and also very interesting, namely the infrared aspects. That's really where all the difficulties occur. But as I said, also interesting things. One of the first interesting things we had seen were the Landau equations. We had immediately started a very general analysis of the diagram with all denominators to see where did these denominators become 0. That's a sign of an infrared divergence. And we had found conditions for that, which were that, I don't write the long expression down, either the Feynman parameter is 0 or the thing it multiplies, the propagator with which it is combined is 0, or the propagator term is 0. Or, and also that we had this derivative condition for all loop momenta and all components of each loop momenta. Why was that again? Who remembers? Why is this important? That's right. So this is when you have the two zeros of D just touching here. This is in the D on the vertical axis and the component here, such that the two zeros, when you look in the integration plane of L9, that the two zeros really pinch that contour, and you cannot escape from being zero. And we had looked at an example of this, the typical triangle diagram, and immediately had come to the conclusion that that was not too difficult to solve if you know how to think about it a little bit. But also, we had looked at solutions of the Landau equations via the Coleman-Norton picture. Slightly odd, but very attractive way of looking at solutions of the Landau equations, using the original diagram, but now looking at it as not as a final diagram in a sense, but as a space-time picture of possible collision processes. So this is a solution by Coleman-Norton. This involved reduced diagrams interpreted as space-time histories of classical scattering with free propagation between vertices. So we had seen that this was okay, but this was not okay. These are two different reduced diagrams of the original triangle diagram. This was okay because you can have two particles, light-like particles, moving in parallel and fusing again. This requires two light-like particles leaving in different directions. You can also look at it this way, two different directions, and somehow having to come back again. But with free propagation between two vertices, that can never happen. But this is a thing that just cannot be a classical scattering picture, and is not a solution to the Landau equations. So, the Landau equations are necessary, are a necessary condition for infrared divergences. Infrared, of course, often mean the collective infrared and collinear. This is a collinear one. And the question is it also sufficient? The answer is no. Need power counting. So it only flags a possibility for infrared divergence, but then you must start counting what are the integration variables in the numerator and the denominator, and is the combination such that it will be a divergence. Okay, and that's where we ended. We still have to, and we're going to start doing that now. Okay, is this picture a little bit clear? This is a bit of a reminder of what we were doing. I'd like to give you a bit of a hint of the power counting here, not as much detail as for the UV case, but to have a quick look how it's done. It's a nice picture also. It's not particularly complicated. You just must look at it in the appropriate way. Oh, this is another. So we'll also see some examples of what I mean with this infrared power counting. Now, one thing before I do that, you can already see in the UV case, the power counting, I have to see if all the loop momenta go to infinity. The measure, the integration measure, and numerator factors will make it worse. Things in the denominators will make it better. But all four components of all loop momenta scale at the same time. They all have to go to infinity. Here in this case, we have that too for the infrared, where all 4 components must go to 0. But in such cases, in these collinear solutions, they don't all go to 0. One loop momentum must go in a particular direction, must go parallel to the outgoing momentum. So it's a bit more tricky in the infrared case. It's not a whole overall scaling, but you must then go to a certain direction and then somehow include it in your power counting. So we'll see that occur. And the typical, always keep in mind, is the integral that there will be some product of loop momenta. I will ignore the Feynman parameters. Won't use them for the power counting. I don't have to do that. Some numerator factor, and then a whole bunch of denominators, depending on the case. Right, so this is the thing you have to keep in mind, a whole bunch of loop momenta in d dimensions. That's what we're going to have in mind. So it is in this very high dimensional space, each of which is a complex integral. Right, that's what the I epsilons tell you, that we have to do the counting. So at the outset it looks like a formidable problem, but it was solved by Sturman in the late 70s in a very elegant way. So the nice picture, the way to think about it, is that we're looking for, in this space, surfaces, well, D-branes you would these days maybe call it in string theory, defined by D is 0 and D and this is 0. Right, the Landau equations in this high dimensional space impose restrictions, and let's call those surfaces. So in that surface of all these integration variables, we can maybe have, let's draw a bit of a surface like this. That's not too bad. And this is a slice through this high dimensional integration space. Now, what variables count towards the divergence or not? Clearly relevant are variables that move you out of the surface or into the surface. How quickly you approach the limit, that matters for power counting. On the other hand, coordinates, variables that leave you in the surface don't matter, they don't change anything. So we must find among the integration variables those that move you away from the surface, those matter for the power counting. Those that don't change anything don't matter for the power, they just leave you in the surface, which is fine. Yeah.
Will you hold the external momenta constant? Is this in general a surface, or let's say for a particular collinear system?
In this case, yeah, we'll hold the external momenta constant. Yeah.
And yeah, so
you can then on top of that vary those two, but here we'll hold them constant.
Yeah, you hold them constant, but I'm asking, is it a surface, or is it really?
No. It's a high dimensional. It's a lower dimensional space than the full dimensional space. If you have a 5-loop diagram, this will be a 20-dimensional space, and this is this reduces you by, let's see, 1, and then you have a number of other conditions that are 0. So it's not always a surface.
Is it that this component which is coming out of the surface is important for predicting this divergence?
Well, let's look at an example and see if your question still remains. That way, that may help you see what's going on. So, so this is the example I'll be looking at is our familiar one, the Drell-Yan one-loop integral, with the momenta, the loop momentum L here. Here goes P1 plus L. Here goes P1 goes in here, P2, and here goes P2 minus L. Now these are the 3 denominators we'll be looking at. And one thing I want to introduce now is light cone coordinates. Familiar to some of you, but let me just define them. If I have V mu, some vector, then I define V plus to be V0 plus V3 over square root of 2. V minus is V0 minus V3 over the square root of 2. And V perp is not 0 or 3, so we think of it as V1, V1, V2. The 2-dimensional component vector. And in terms of these vectors, v squared is minus 2v plus v minus plus v perp squared. The nice thing of this notation is that in this way, not all components occur quadratically. The plus occurs linearly and the minus occurs linearly. Sometimes that's useful. In fact, it will be useful now. So in these terms, I'll let p mu, the p1 mu, coming in along the positive z, moving in the positive z direction. So it will be some scale q over square root of q over 2, 0, 0, q over 2. So that's, I choose a frame where p1 comes along the positive z direction, and p2, it won't be a shock, along the negative z direction. So those are the normal way of labeling momentum. Now in the light cone language, p1 plus will be q over square root of 2, and p1 minus and p perp are 0, and p2 minus will be square root of 2, and p1, 1, 2, and the other components are 0. So you see here that in plus minus light cone notation, these momenta only have one non-zero component rather than two. So that's a useful thing. So that's our notation. We will also use that d4 of L can be written as dL plus, dL minus, d2L perp. I will probably now and then confuse perp and T. It means the same thing. I mean, just flip the perp sign. It means transverse. Okay. So we have now in our example 3 denominators. D1, which I'll call L squared. D2 is P1 plus L squared. And D3, P2 minus L squared. Right. So let me write those in light cone notation. The first one will be minus 2L plus L minus plus L perp squared. This one will be minus 2P1 plus L minus minus 2L plus L minus plus L perp squared. You see P1 has only a plus component, so it combines with a minus of L. And that's the only term that contains the P1. And for D3, this will be 2P2 minus L plus minus 2L plus L minus plus L perp squared. So this is the stage. We've set the stage, we defined the variables, and now we can do some power counting for each of the 3 solutions we found. In fact, we'll do only 2, because the third one will be more or less a copy. Let's look at the soft solution. The soft solution corresponded to all 4 components going to 0. And at the pinch surface, we have, of course, that D1 equals D2 equals D3 is 0. And now we must see if we vary other L's that, if we vary them, will not change anything. So those would be the intrinsic coordinates, and you also have the normal coordinates as intrinsic and normal variables. So my claim is that there the normal variables are L plus, L minus, and L perp, all four, and there are no intrinsic variables. There's nothing that I can change that does not move the d's away from 0. If I vary L perp from these terms, d becomes non-zero. If I move L plus and L minus a bit away from L minus away from 0, I'll vary d2 away, and that's already enough to move away. If I vary L plus, d3 will move away from 0. So they're all change d's away from 0. Okay, so this is a bit of triviality. And what we do, so we define the normal variables to be these. So then, keep in each d the leading term in normal variables. The normal vars. So these are small parameters, these LU, so let's keep only linear terms or 0th power terms, but if there's any higher power terms, we can neglect them. So that means that d2 will be, if you look here, we only keep the first term, because this is quadratic and this is quadratic in the normal variables, this is linear in the normal variables. So this will be minus 2 p1 plus L minus. By the same token, d3 will be 2 p2 minus L plus, and d1, there all three terms contribute. They're the same power. All two terms, they're the same power. And the resulting integral this is called the homogeneous integral. I will be d4L, sorry, it will be dl plus dl minus d2L perp divided by, well, these three approximated integrals, 2 1 plus 2 p2 minus L plus, and then the whole L squared. And now we can do power counting. We have now a form where all terms are homogeneous and we can see what it behaves like. Remember, we have to go through all these momenta to 0. These are the normal variables to see how fast we move away from 0. Well, we have 4 powers upstairs. And here we have 1, 2, also 4. Right? So this is log divergent in the infrared. Okay. Okay, but that was a bit of a, this is also called, by the way, the iconal approximation. It'll come back in future lectures. To illustrate the power of this, let's also look at the other pinch surface, the collinear pinch surface. So we look at the collinear one, pinch surface. So where L mu must become parallel to P1 mu. So my claim is the normal variables, I'll write the claim down first, will be L minus and L perp squared. And the intrinsic variables will be L plus and phi, the azimuthal angle in this two-dimensional space. Well, let's see if that makes sense. So we're now looking for the case where L is parallel to P1. So at the pinch surface, L mu only has a plus component, as some is L plus only. This is a bad mathematical notation. I can write it as delta mu plus times L plus. Right? So it only has a plus component at the pinch surface. So indeed, you can check that all these 3's are 0. All these 3D's are 0. Now, suppose I have this at the pinch surface. If I change L plus a little bit, nothing changes. Right? All the D's will still stay 0. I just move a little further with a bit more momentum in exactly the same direction, in the plus direction. But all 3D's will still stay 0. So that's why this is an intrinsic coordinate. Right. Also, if I already am in the plus direction, if I then do an azimuthal rotation around that direction, it doesn't change anything. Right. The only L perp squared occurs. So that's an intrinsic variable. Now the other two, if I change L perp squared, obviously it changes away from 0. And if I change L minus, then I certainly pick up this term. When I move that away from 0, L minus, this becomes non-zero too. Right, so we have now a different situation, and we can see what the homogeneous interval is. So I will now go to, when we first write here the intrinsic variables, dl plus d phi, and then here the normal variables, dl minus dl perp squared. Maybe there's a factor of square root of 2, but for the power counting that doesn't matter. And then we also have to see what the d's are. Well, d1 will be behave like again the whole d contributes, because this is normal and this is normal. They're both linear in normal. Now L perp squared is normal. So d1 still behaves like minus 2 L plus L minus plus L perp squared. d2, when I keep only the leading term in the homogeneous interval, will be also again the full expression. So it'll be minus 2 p1 plus L minus 2 L plus L minus plus L perp squared. All three terms are linear in the normal variables now, in contrast to the soft surface. And d3, what will that become? What's the leading term there? Sorry? No, because those are linear in the normal variables. But this is the lowest power. This is 0th power. No, that's even bigger. Right? This has no power of the normal variables. So when I take the normal variables to 0, this is the one that remains. I must always take the leading power. The leading power can be the 0th power. So that would be just 2p2 minus L plus. So that I can write down here, 2p2 minus L plus, and here I write the other two, L squared and well, this d2 variable. And now we can do power counting. This prefactor won't matter, right? It doesn't matter what these variables are. You stay on the pinch surface. So this doesn't matter the prefactor for power counting. But here we have 2 powers upstairs of normal variables. And this is linear in the normal variables, all 3 terms. Or all both terms. And d2 is also linear in the normal variables, all 3 terms. In L minus, L minus, and L perp squared. So this is plus 2, minus 2, again log divergent in collinear in one direction. So indeed there is a collinear divergence in this interval. It looked, the Landau equations had indicated that might be so, but now we've proven it by power counting the solution. But you see, here the power counting is really direction dependent because we're dealing with a particular direction. but not necessarily that more difficult than UV power counting. Just if you phrase the problem in the right way, then it yields to analysis. Okay, is this clear? I don't think it's too hard if you look a little bit at the variables. So let me immediately give you, if you
Can you just repeat that how this is logarithmic divergence?
sorry,
Just repeat how that is logarithmic divergence.
why is logarithmic? So we have these are the normal variables. They move you away from the pinch surface. There are two powers upstairs from the integration measure. Remember, L squared is one variable. It's not the variable squared. L squared is the variable. So plus 1 plus 1. And this denominator is also linear in normal variables because of the L minus and the L perp squared. L plus doesn't count. That can be as big as it wants to be. And this one is also with L minus, and L perp squared. Linear in normal variables. The L plus and the P plus don't matter. Right? So this can be done very systematically. And I think this is really Sturman in 78, a beautiful paper that is really worth reading in PRD. And the outcome, let me just write it here. So let me draw the most general class of reduced diagram that is indeed corresponding to an infrared divergence or a collinear divergence. So Sturman-Indus analysis looks at all possible reduced diagrams and then power counts them all by clever choices of normal and intrinsic variables. And the outcome is, for the Drell-Yan, a virtual correction to all orders, at all orders. I just have to make a drawing. They all look like the solutions we found to all orders in perturbation theory. So the blob stands for arbitrarily complicated, so you could have something like this. Yeah, and then same thing here, 15 collinear gluons all exchanging, and then you can have all kinds of soft gluons, maybe with a fermion loop connecting. All these momentum must be zero at the pinch surface, infrared. These are collinear and these are anti-collinear directions. All the ones that matter have this form. This is a general graphical representation of all singularities. It's extremely powerful. It also represents a kind of factorization. The sum of all these diagrams is, in some sense, this product combination of blobs. Each blob is really a summary of lots of possible diagrams of this shape. So in a formula, this looks like, let's call this, we'll label them J1 and J2 as J1 mu1 to mu n, J2 mu1 to mu m, and then S mu1 to mu n, mu1 to mu m, and then times the Hart function, all consisting of all the diagrams, all the lines are off shell, where all the reduced diagrams have been shrunk to a point. All those lines that have been shrunk to a point sit in H. The ones that stay lines, that stay on shell, are here, and these are all the lines that have been shrunk to a point. So there's any number of gluons can go across. That's why I have some kind of multi-index tensor here and a multi-index tensor there, and well, it also must be connected to this, whatever this J is. Right, so nice, but at the moment still fairly useless. I mean, if you go 15 orders higher, there will be more indices, and it doesn't really help you. But it's a great start. So can this be further simplified?
What is that S?
Sorry?
What is that S?
S is for soft, and J stands for jet. So soft solutions there. So in our very first example, this whole blob was just one soft gluon going from one line to another. It's a very trivial form of this. Simplified means that I would really like that I have not this complicated tensor combination, but I have a function J times a function S, J1, times a function J2, times a function S without indices, times H. Just a simple product. That would be really cool. So that's what I mean by simplified, i.e. we have to look at jet soft factorization. Can I somehow decouple soft gluons in an interesting way from these jet-like, these hard lines all moving in the same direction? Now that is a very long and complicated analysis, a subtle analysis, and I'll just give you one instance of it, which is kind of nice, again associated with the iconal approximation, just to see how it's done. So let me do that here. What I'm actually working towards is giving you a sense of what is behind the proofs of factorization. We had the Parton model, which is in a statement. A hadron collision crosses is 2 PDFs and times the partonic cross-section. That was this assertion. But now we're dealing with QCD, interacting theory. Is this formula still true? And that's really what this is moving towards. That's the formula that everyone uses to make predictions at LHC or any hadron collider, so it's worthwhile paying a bit of attention. You don't get this in many other cases. So let's look at factorization. So let's look at a case where we have an incoming fermion and emitting one gluon into some, say, soft process. And we're just focusing on this part. This is the jet-like line. So here comes momentum P. Here goes momentum P plus L. And the soft momentum, all 4 components of which are nearly 0, come in from here. And P has mostly a plus component. So it's a jet-like line. But let's first write down an expression for this situation without worrying about if things are large or small. We just write down, we have to go against the charge flow again, so we start with an expression J. Whatever this is, this blob, I'll just give it the name J. And then we have here this bit of propagator. That would be minus I P slash plus L slash divided by P plus L squared. And then we have here the vertex, GTA gamma mu, U of P. That's for the polarization spin at the end. And then times S mu, which depends on L and probably lots of other stuff. That's this blob. So the propagator here I also include in S. Who remembers what the TA here is? That's a generator. And that lives in a different space. I can really put this in front. It doesn't couple to anything else. The G is, of course, a number. I can put this in front. Okay, so this is the situation. Now let me look at the approximations. So L mu, all 4 components are 0. So we're going to first neglect this term because it's smaller than P slash. And this term here, well, L squared, that's subleading in the soft momentum. So I just approximate this by 2p dot L. Okay, now, so I have the following situation: minus I, G, T, A in front, J, and then P slash L slash, sorry, not L slash, P slash gamma mu, U of P, divided by 2p dot L. Okay, this is after the simplifications. Now comes a very nice thing. If you see it, it's immediate. You see, if this were in the other order, it's 0. Because P slash would stand next to U, and that's 0. That's the Dirac equation. Right? So that means I can, for free, write the anti-commutator here. That's a free result. And who knows what the anti-commutator of P slash and gamma mu is? That's just 2p mu. Do people know this? Work this a little out. It's just a Clifford algebra. So this is 2p mu, and then this can be taken out in front. There's no more slashes and spinor indices. So this is minus I GTA 2p mu over 2p dot L times J U of P. Times S mu. And the way I can graphically draw that is by having this is J mu, as if there was never a gluon being absorbed, times this prefactor, but that sort of is a product. So let me draw a double line for this particular propagator. It's not a full propagator. And the coupling is not with a gamma mu, but with a p mu. So typically people denote it with a little circle. And here is then S. So this combination corresponds to this combination. So all that S knows is the direction of the original momentum, even the size scaled out. And it is really factorized. I mean, it's a multiplication.
Can you go through that again? So there's a jet and the spinner which connects to it.
Yeah, this has a spinor index, this has a spinor index.
And well, S mu has the gluon propagator intrinsic.
Yes.
And
That sits outside.
so and the 2p mu is a coupling to which?
That's what S mu couples to, right? Mu, mu. So this line here corresponds to downstairs 2p dot L, and the little open circle to p mu. That's sort of a vertex. It has a mu index. But it's a very simple vertex. This is called an iconal vertex. It is again the iconal approximation, actually, just as in the other board. But it really is a product. This is no more has no spinor indices thanks to this identity.
Does the factorization fail here at any point?
Sorry?
Does the factorization fail here at any point?
No, it also works then because there was an extra mass here then. And then that's the Dirac equation still works. Yeah. Oh, let me just leave this. So the result, I'll just write it here. If you do the full analysis, is these jet-like lines, but then a product of all these soft gluons attaching to such iconal couplings. So this keeps on happening. So these things are completely now unaware of any soft gluons flowing into these lines. It just becomes a function by itself. So I now combine these factors together with S, and it just becomes a product. So I get, indeed, J1 times J2 times S times H. Simple product. Sorry?
Are you considering soft solution?
Yes, this is what this S means, right? All these singularities by power counting are of this type, where you have soft gluons being exchanged or at least coupling to these jets. So gluons with all four momenta near zero. That I've told you that that's what we found in one loop, that persists to onwards. So it's a solution like this one. Right? So this is really nice. This is for all the virtual diagrams for Drell-Yan. And nice as though it is, if you add up all the real emission bits to the cross-section, there's more than virtual diagrams alone, more than loop diagrams alone. And it would not even work at all for that. It was useless analysis for cross-sections. But it turns out this same analysis holds true for all diagrams, including real emissions for the cross-section. By more or less the same methods. So the same factorization holds at the cross-section level. After summing over all diagrams. This has a side benefit after summing over all diagrams, that in fact the function S for the cross-section is 1. So here we found some function S. There's also a similar S if you have real emissions. If you add all those up and you're not too close to threshold, then S turns out to be equal to 1. It's a beautiful analysis also in the papers of Collins, Soper, and Sturman. And I'll call these J's, right? These are incoming parallel lines. But that's really nothing else than the partons inside a proton. They all move in a parallel line. So what we actually have proven is that the cross-section for Drell-Yan to all orders can be written as phi. I've now switched notation from J to phi to indicate we're dealing with parton distribution functions. Phi 1, phi 2 times, and then I won't call it H anymore, but sigma hat. A very schematic form of the parton model, but now actually in terms of fully interacting theory. So this is how you prove factorization of hard scattering at the LHC or in any other hadron collider. Let me give the bit more precise form of this. Now with QCD effects included, but it won't look very different from what you know from the parton model. Then sigma hat. And this is, sorry, I, J out of P, I out of P, sorry. These are parton of type I out of P, J out of P. Psi 1, psi 2, Q squared. Do you see any difference with the parton model formula that I've given you? I should also say here I have alpha S of mu and possibly mu. We're dealing with an interacting theory now.
But this is our assumption.
No, it's a proof.
Can you just non-particle data phi 1, phi 2 and with the mathematical calculation sigma hat?
No, that's what I was. I gave you arguments why it's true. It's not an assumption. I've tried to prove it. Yeah. That indeed all the jet-like lines decouple from the soft lines and from the hard part, H. And this is what is left. You see any difference with the Parton model formula? That's right. There's an extra mu dependence in the PDFs. That we'll see later why that occurs. I'm just telling you that is an upshot of this analysis. The same way that looking at higher orders in QED led to mu dependence as well. When the renormalization, okay, you had to work to get rid of these UV divergences, but as a feature or bug, mostly feature, you get mu dependence in various things. It allows you to vary scales of things. And this is similar. Here the proof getting rid of infrared and IR divergences also introduces a mu. It's a slightly different mu even, but for the moment that we call it mu. Alright, so that's the upshot. Now, the question, is this exactly true? This is not exact. This is valid up to corrections. And it cannot be order alpha S corrections because we tried to include close to all orders. This is valid up to corrections lambda QCD squared over Q squared. Q squared is the hard scattering scale. So power corrections, not 1 over log corrections. So all the alpha S stuff sits in here, but the whole thing is true up to such corrections. And this is really small. I mean, lambda QCD is, say, 0.2 GeV, so the square is 0.04. For, say, the top quark, Q squared is 10 to the 4th. So you're looking at 10 to the minus 6 corrections there. So that should be very, very small. There are cases, sometimes the lower energies, where you will start have to worry about such power corrections. They do start playing a role, also known as higher twist corrections. But we will certainly ignore. Now, so this, I think, hope to give you a bit of a sense of what's behind this Parton model formula in the context of QCD. Until when shall I continue? Yeah. So, and I've mostly given you examples from loop diagrams in virtual calculations. Let me now turn a bit to real emission diagrams. So let's now look at IR and collinear divergences in real emission diagrams. Often I leave the word emission out. I would just call it real, the real part. It's a bit. So we had at the loop level, we had, just to remind you again, we had that this could be in the infrared and the collinear and possibly also collinear infrared. We had something like this, right? This is in the 4-dimensional loop momentum space. There are regions where the loop momentum looks like this, and this had an infrared divergence. And even infrared collinear divergence. Now, in emission, we're dealing with such an emission, and we have to integrate over this momentum, not because it's a loop, and you must always integrate with loop momentum, but you must integrate it because it's part of the phase space, and you must integrate it with things you cannot measure, and if you cannot measure the gluon, you must integrate over its momentum. So this could be, let me draw it a bit cartoonishly, where the gluon is emitted very, very linearly like this. Almost perfectly parallel to the incoming quark that emitted it. Right, you can imagine that. Now, in that situation, so if this momentum is K, this is K, and here comes P at the outset, and this propagator here looks like P minus K squared. Well, something in the numerator, but I'll focus on the denominator, P minus K squared. Now, if K becomes very, very parallel to P, and P squared is 0, because it's a not-shell momentum, then you see that also in this case you have a danger of being infrared divergent, 1 over well, if k gets more and more parallel, it's get 1 over 0. So also in phase space intervals, there's certainly a risk of infrared divergence. So I'd like to set up before the break the situation a bit and then continue it after the break. So let's have a closer look. So in Drell-Yan, there are two Wheeling emission diagrams. Well, it won't be a surprise. We have one. Here's our off-shell photon, and here's one. And of course, the other one is, yeah, when it's radiated off the other line, right? And we must sum those, and only then afterwards square. So let's call this diagram A and this diagram B.
Sir, outgoing photons are emissions photons are soft. Yeah.
These are gluons.
Sorry, no,
Yeah.
photons are soft.
At the moment, not yet. I'll take that limit in a moment, but for the moment, I'm just writing the general case. And then, well, this is P1. Here goes K. So this is P1. So this is P1 minus K. And here goes P2, and this is P2 minus K. So the scattering amplitude, or the invariant amplitude, is just the contribution of these, both of these diagrams summed. And how do they then contribute to the cross-section? The cross-section says that this is equal to some constant. And constant contains all the spin averaging and the color averaging. I'm not so interested in that now. Let me call it part of C. This is the flux factor. And then dnq1 over dnq. This is the integration over the off-shell photon. I will also not be too interested in that. And here is the phase space integration of the gluon momentum. And of course, the gluon momentum must be on shell. It goes in the final state, so it's k squared is 0. There's also a factor for the off-shell photon with a sort of mass big Q squared, and then a 4-dimensional delta function that implements all the complete momentum conservation. All of that is his phase space, and this you should be a bit familiar with, times absolute value of m squared. Okay, so that's the setup, and after the break we'll tackle that a bit and see indeed a nice form coming out, which will be helpful in understanding the situation in the Wheeling emission diagrams. Is again part of the Eikonman approximation, and we'll see it's also a first step towards things we'll do in the remainder of these lectures towards moving towards resummation. So to illustrate the emergence of logarithms in the phase space. So we're still in the story of infrared and collinear divergences, the most interesting part of QCD. We've done all order analysis, first the factorization and loop diagrams. Now we're moving into looking a bit more at phase space and see what we learn there. And talk about real observables, things you can measure. Any questions so far? No? Okay, let's have a 10-minute break. Okay, 10-minute break.